Welcome to this video, which will be used to demonstrate how we can find the derivatives of exponential functions base e. So most importantly, you'll probably get a sense of what this base e is that I'm referring to. So right now, this would be an exponential function base 2. We should be somewhat familiar with some of its properties. So for example, exponential functions have this kind of general shape to them here. They all pass through your point here, 0, 1, right? Because it doesn't matter whether your base is 2 or 200, anything to the 0, if x was 0, would always pass through that point, 1. And then you'll get this. This would be an example of exponential growth. Well, our goal today is to look at how do I find the derivative of this type of function. So if you come across some type of function and you're not sure how to find its derivative, you could revert back to what we refer to as the definition of a derivative, or the first principle of calculus, which is this formula: limit of f at x plus h subtract f at x all divided by h as h goes to 0. So let's try and take the derivative of some exponential function. We'll just make it generic, where a is some element of the real numbers, and we'll assume that it's a positive base for now. A is greater than 0. So the derivative, by definition, so remember, if this is f of x, right, there's f of x plus h simply means replace the x with x plus h, which I've done here. And then we end up with our formula filled in. So now we've got to try and manipulate this. I notice I have an a to the x plus h and an a to the x here. So a to the x plus h, based on laws of exponents, if you had a to the x multiplied by a to the h, it would be the same thing. The bases are the same. It would be a to the x plus h. So we're just going to kind of work backwards and say, well, if I have a to the x plus h, I'm going to write it as a to the x multiplied by a to the h, subtract a to the x. The reason I would do that is it gives me now a GCF of a to the x, which I would take out. Now, as h goes to 0, that's going to have no bearing on a to the x. This is the variable h, which we're going to make closer and closer to 0, which again will not affect this. So what we're now at is that f prime of x is a to the x. I just jumped that out to the front because it really doesn't, h going to 0 has no bearing on that. So that comes out to here. And I'm going to have that multiplied by this limit over here. So right now, if we were to find f prime at 0, right, oops, moved on me, sorry. So f prime at 0 would mean fill in 0 for x. So it would be, and if you notice up above here, it's a to the 0 multiplied by the limit as h goes to 0 of a to the h minus 1 over h. So a to the 0 is 1, then multiplied by whatever this value would equal, a to the h, oops, a to the h minus 1 over h as h goes to 0. Now in terms of a slope, f prime is slope of a tangent drawn to the graph at x is 0. So this, assume this was y equals a to the x. If this were the tangent drawn at x equals 0, the slope of this line would be f prime at 0. Right, because up here, right, we know that f prime derivative means slope of a tangent drawn to the function at that particular point. So this is kind of visually what f prime at 0 is. It's the slope of this. Well, the slope of this line then has to turn out to be the limit of a to the h minus 1 over h as the h is approaching 0, because that's what f prime at 0 turned out to be, this expression. So the dilemma we have is it turns out here that the f prime at 0 is this limit right here. So therefore, f prime of x is your a to the x multiplied by the slope of the tangent at 0, because we just said that that's equal to that whole limit of a to the h minus 1 over h as h goes to 0. Well, if you were to look at a couple of numerical examples, so suppose we did base 2. Well, this time, if you put 2 to the h minus 1 over h, and you make h become closer and closer to 0, you get about closer and closer to 0.69. If I pick 3 and use 3 as my base, you can just see some calculations as I make the h value get closer and closer to 0. You can see that I'm getting about 1.09, 1.1 roughly. Well, that means that there must be some base that we could choose that has to be between 2 and 3, such that these this value would get closer and closer to 1. Because if that was the case, then we wouldn't even need this expression because it's just equal to a 1. Well, so back many years ago, when they first kind of were working with these derivatives of logarithms, they said, well, let's find a base so that when we do this calculation, this turns out to be a 1. And that number turns out to be a mathematical constant that becomes quite popular as you get into the higher level math program. So again, you haven't run into it until now when we're talking about calculus. So this is a really kind of more complex or higher level type of study you would get into with logarithms, where you would use what's called Euler's number. And the reason, someone says, well, what's so significant about Euler's number? Euler's number is the only number that when you take this number, 2.718218, and it does go forever, it's like pi, it's irrational, non-terminating, non-repeating, but it is the only number that when you find the limit of e to the h minus 1 all over h, as the h gets closer and closer to 0, this gets closer and closer to 1. Now, I don't know if any of you see the significance of this yet. There is a button on your calculator. Usually on most calculators there's an log button, common log, and then above it will be like a 10 to the x button. And then there will usually be right either below it or beside this an ln button, which is called natural log. And then there'll be an e to the x button as your second function usually. So if you wanted to know what e, say what is this e, this lowercase e represented, just take and go second function this, put a 1 there, e to the 1, it'll spit out this, it'll fill your screen full of digits. And that is Euler's number. It is pronounced oil, like oil you put in your car. Named after a German mathematician. I think it was Leonhard Euler was the founder of this number. Okay, well now that we kind of see what Euler's number is and hopefully have some sense of why they found it, and again it had to do with logarithms and derivatives of logarithms, here's what we now know. Because according to definition, if someone says what's Euler's number? It is a number such that this limit is equal to 1. So, well, what's so special about that? Well, what this means is that because of our definition so far, if we had y equaled a to the x, we found that y prime was a to the x multiplied by the limit of a to the h minus 1 over h as h goes to 0. If I change a, right, if a is e to the x, then my derivative becomes e to the x limit of e to the h minus 1 divided by h as h goes to 0. And e, base e, is the only base where this expression becomes a 1. So essentially that disappears. So now y prime will just be e to the x. And that's the significance of base e, Euler's number. It is the only number that when you find its derivative, or slope of a tangent, when x is equal to 0, it turns out to be a 1. Any other exponential, so we looked at 3 to the x, and we had done 2 to the x. 2 to the x was 0.7 roughly. 3 to the x was 1.1 roughly. So if you have any other base, you're going to get some kind of an ugly number that you're going to have stuck at the end of this, which is why they uncovered base e for us to make derivatives of exponential functions much easier. So that's why you're going to find from this point forward, if you continue studying some calculus, that most logarithms will no longer rely on base 10 was what they called the common logarithm and used most frequently in our pre-calc studies. Well, now that'll switch and become base e, Euler's number, for the reason that I've outlined here. Okay, well, now that we've got that ironed out, let's identify a rule here. So if you have e to the x, the derivative of e to the x is just simply e to the x, because remember that limit that would go here beside it, we determined that that was going to turn out to be a 1, so it doesn't even show up. It's the only function that is actually the derivative of itself. E to the x, its derivative is also e to the x. Now, if you get more general, we've used this notation before, the derivative of e to the u. So let's suppose that the exponent here is not just x, maybe it's 2x, maybe it's x squared, maybe it's cotangent x. Well, then this rule gets extended a little bit to become e to the u multiplied by the derivative of u. And if I just extend here, so what does this mean? This means that if I have the exponential function y equals e to the 5x to the 4th, then my derivative is e to the u multiplied by the derivative of u. Y equals e to the cosine 7x to the 4th. Y prime is e to the u multiplied by the derivative of u. Should be negative sine 7x to the 4th times the derivative of that, which would be 28x cubed. So what you now know how to do is take the derivative of an exponential function if the base is e, Euler's number. Now this is going to be kind of a trigger to allow us to now come up with how to take the derivatives of logarithmic functions and some other exponential functions to any base. So eventually we'll have a rule that will allow us, or rules that will allow us to take the derivatives of any exponential function to any base and any logarithm to any base. However, this will be kind of the stepping stone that gets us pointed in that direction. Alright, so if you've been maintaining a page that you have as your differentiation page or rules of differentiation, which I suggest you do if you haven't already started, add this now to your list. So the derivative of e to the u is e to the u multiplied by du. Alright, thanks for watching, and you can be able to find some practice of this and keep on moving towards getting the rules to differentiate all your other transcendental functions. Thanks for watching.